Hi, I'm Dr. Lewis. This is a tutorial on how to do a finite impulse response filter with the windowing method. Before we get in how to design a filter, I just want to briefly discuss or describe or explain what the time domain is, the frequency domain is, why we need filters, what is a filter. Maybe you'll understand the maths better. Then getting to the maths. Maths is easy. Mathematicians know this. So not to look bad, they give it Greek symbols, give it made up words so that maybe they look more intelligent than they really are. I think the idea behind this was to get some goals, but this was an epic fail because you don't get a mathematician with a pretty goal. Alright, let's look at a time domain signal. Here we can see there's a time domain. We can see it looks like a sine wave. This is a sine wave, and we can see it's ramping up. This is supposed to be the audio range of what a human can hear. At the moment you can't hear anything because for one it's not near my microphone, and the other this is a very low frequency. You need a very big speaker to be able to play this low frequencies. If I zoom it up a bit, I'm going to make you listen to it a bit. So there we can see this is how a sine wave look like, and this is how it sounds like. As I said, this can be sound, as you heard now, or this can be information from a sensor that will mean something like temperature or level, or maybe information from a Formula 1 car shock. So it all depends on what the physical input is connected to. Alright, let's talk about the maths a bit. Here we can see there's just a Mathcad sheet that I've designed, but what there is not really important. What I just wanted to show you, this is the normal sine wave formula that you did in school. Here we just plotted the normal sine wave formula. This is of a specific frequency, and if we have more than one frequency of a second frequency, this we can see it's now a higher frequency. So this was just a simulated signal just to show you how a pure sine wave would look like. But the thing is, we don't normally get pure sine waves. It's normally a combination of these sine waves that will make a certain sound. For instance, if we do processing on sound processing. So if we look at, let me just open another example here. If we look at this one, there, what we do here is here we have 3 sine waves of 3 different frequencies, maybe 1 Hz, 3 Hz, 7 Hz. This is how the 3 sine waves look like. There's my slow wave, the faster one, and the quicker one. If we add them together, then this should start looking familiar. There we have the type of noisy signal that you normally get. So for instance, if we, this is just simulation. If that's the information you're expecting, but you're getting something like this, it means there's a noisy part on it. And by doing, in this case, we did a discrete Fourier transform, or a fast, you can also do a fast Fourier transform. By doing a fast Fourier transform, it's going to bring you into the frequency domain. So you can Google fast Fourier transform. It converts a sine wave, where we have 3 sine waves added together. It's going to give you 3 peaks. And these 3 peaks will tell you what the 3 frequencies are. And if you only want that one there, or only that one there, you can either design a low pass filter or a band pass filter that will only let that frequency through, or a high pass filter. Okay, if we talk about the pure sine wave again, if you look at this clip, remember this clip where we had a pure sine wave, and we listened to it a bit back. Let me just play it again. You can definitely hear that sine wave, the higher the frequency, the higher the pitch, or the higher the note. But a pure sine wave doesn't sound true. It sounds a little bit fake. Most things in nature has got a combination of frequencies, where the main frequency would be for this note, but the rest is just to, let's say, color it in and gives it a certain value, a certain sound, so that it sounds like a piano, or it sounds like human's voice, or it sounds like something particular. So let's listen a bit to Rocky Horror Picture Show. If you know Rocky Horror Picture Show, you know Tim Curry and Susan Sarandon. Their voices are at the end of the spectrum of each other. So let's quickly listen here to Tim Curry.
I see you shiver with anticipation. So, come up to the lab and see what's on the slab. I see you shiver with anticipation.
So what we can see here is this is a time domain, there's a sine wave, this is the frequency domain, this is the specific frequency, so now strong the amplitude is, and we can see that these voices are at the lower range of the frequencies. So it's the same note, it's a note that is singing, but we can see there's a combination of frequencies of which is in the lower value. If we listen now to Susan Sarandon, she's got a higher pitched voice, and we can see that the voice is definitely in the higher range of the frequencies. Alright, if we look at, we've seen now the sound processing, or how sound look like. If we look at sensor inputs, they work on the same way. If we look here, that green is what, and I just screenshot this from the internet, the green is what they wanted to measure. The red is what they're actually measuring. The blue is averaging filter. I suspect that they tried to get the noisy measurement as close as possible to what they're actually supposed to measure. So if you want to design a filter for this, you first have to analyze it. So you record a bit like they did, and then you do the Fourier transform on it. So the Fourier transform will look at this frequency. It will assume that this will go on as a sine wave, so it will calculate, well, it will calculate what frequency that is. It will also calculate what frequency the red one is, the high frequency is there. So you would immediately expect, you know, something like this, where you have a peak at your low frequency, a peak at whatever noisy frequencies there are. So you'll see where your noisy frequencies are to design your filter, make the best boat plot for your filter. Just remember that your filter must be, try to do it as the quickest this will change, the quickest that will change. Remember, Nyquist rate, that must be at least double that. So this is typically where a boat plot comes off, the name boat plot. Boat plot is a filter's boat plot, is where it's supposed to be in your frequency domain. So if you look at this one, if you want a low pass filter, it means we're typically, and you've seen this before, there's a line there and it goes down there and it takes off this. So the boat plot will mean everything under that line must go through, everything that's, if it goes down, then everything else must be made softer or taken away, so that you're only left with the frequency that you're really interested in. So back to sound processing. Let's take an example where we might use something in sound processing. If we look at the Who, I don't know if you know the Who, band of the 70s, 60s. This is typically one of their performances. They had big sound systems. In any live type of show, you'll have a large sound system on the side. This is an example of what they have. So they had big speakers, which will be play the low frequencies, mid-sized speakers that will play the mid frequencies, which is normally voice and so on, and then the high frequencies that will make, you know, color in the sound, as to say, so that it will actually sound realistic and not fake as a pure sine wave would. So typically this big systems, there would be an amplifier for each speaker, which normally in this open air type of stuff is a generic amplifier. It's not designed specifically for a specific speaker. It can do either a bass or a mid or a high. So you need to do some pre-processing, and normally at this live shows there is digital signal processors that you assign After the mix board, all the instruments will go to the mixer board, and then it will go to the specific speaker, to a specific amplifier. And just before that specific speaker amplifier, you must tell that speaker either through a low pass filter or a band pass filter or a high pass filter what it should play. So for the bass speakers, you'll first send that speaker's amplifier's information through a low pass filter, so that that speaker only plays the low frequencies which is best designed for. Same with the mids, same with the highs. So the high frequencies, before the amplifier for that speaker, you'll do some pre-processing, and it must be point by point in real time. That will do a high pass filter on that, and this is what we can design also a FIR filter for. So it's not just sensor inputs, it can be audio as well. Right, let's go back to the presentation. So for finite impulse response filters, we see now why we need to filter. We've looked at the frequencies, we looked at the time domain, the frequency domain, and I explained quickly a Bode plot, so that we know what a time invariant signal is. So it's as the signal come in, there's a signal going out in real time, and time invariant. We know what a causal system is, it's going to be a filter. And these are the two types of structures you get. You get an IR structure or a FIR structure, so infinite impulse response or a finite impulse response, and this is now going to depend on what type of language you program in. So keep the structures in mind depending on what language you program in. Alright, so let's look at the structure. This is where your signal will come in, or your values will come in. That's where your answer will come out. These are all delays, so it's a shift register, or if you do different type of programming, it's a serial in parallel out type of processor. So this is the formula for it, and we can see again what I said, Greek symbols, which means nothing. It's add, you just add. This symbol means add, so you take whatever comes in, you multiply it with that one. This one sample back, this one stores the previous sample. So if this was 5, then the next one was 10, then it means if the next one was 10, you got 10 here. If the previous one was 5, 5 would be there. So you get 5 times that value, 10 times that value, and you add them all together. Can you see it's just normal add? So in your language, you have to program the structure in your language. So in LabVIEW, you can wire it. In assembler, you'll probably have to store these in temporary registers. So you have to name that the temporary register, times it with these constant values. In C or Java, it might be a different way. Maybe you want to just program the formula instead of the structure. But keep in mind how it's going to flow, because you have to program this in whatever language, programming language you're working in. Okay, as I said, you probably used the structure before, you maybe just didn't realize it. If we look at a sine wave, maybe this is the values coming from your temperature sensor. This is your average value. Let's say these values were, let's say it was 2, 3, 2, 3, 2, 3, and so on. What you normally would have done is to get the average, you would have said 2 plus 3 plus 2 plus 3 plus 2 plus 3, and would divide your answer by 1, 2, 3, 4, 5, 6. So if you divide your answer by 6, you get the average value. This is a running one, so as the new value comes in, it will take the previous values and then add them together and get the average. So if we look at the structure, let's say this is shift registers. So this value, let's say this is your last value that you got. It means there was a 3. Let's say the values are entering now at the moment. So we've got a 3, then the next value would be a 2. So this 3 will move over to this side after the shift register. So this is one sample back of your program. So the new value is 2. Then after the 2, we know that the next value would be a 3 again. So this 2 must move over to this side. The 3 that was here will move over to that side, only keeping me the 3 that is there now. So when the next 2 comes in, it means this 3 will move there, that 3 will move, that 2 will move there, and that 3 will move there, filling up this shift register. So this is your what you normally call serial in, parallel out type of processor. So you can, depends on what processor you program or language you program in. This can be assembler, we have to store this in temporary registers, or in Java or so on, we have to do serial in, parallel out type of processing. Then we also divide them by the amount that we have. So how do we get that right? Well, you take that value and you multiply it with a comma, with a fraction. So it depends on how many values you have, you multiply it with that fraction, so you don't have to add it up at the end, getting an averaging, which is in this case a low pass filter. Can you see, because you're getting the averaging, it's going to give you the low frequencies in it. So you can see it's an averaging filter, and by now you probably thought, okay, that's very well, but how do you do a high pass filter? Now if you look at mathematically, if you want to increase your peaks, then it means you have to add this one with that one with that one. So if you do your calculations right and you say, maybe I want to add this one with a big multiplier and that one with a big multiplier and these with maybe no multipliers, if you do this coefficients the right way, it's actually not going to take the average, it's going to increase this peaks, making it a high pass filter. It's increasing the higher frequency, if it makes sense. Alright, so let's talk about filter design. This is, remember the Bode plot, so this is a frequency spec. So we can see this is a typical low pass filter. We want all these frequencies to go through and those frequencies not. So there's just a few definitions. This is the pass band, so it means these frequencies must go through. Transition band, so it's from the part that you want to go through to the part that you don't want to go through. You can see the amplitude is going down, so some of these frequencies might still slip through if you don't want them. And then the stop band, that's the part that you don't want to let through. This will mean a Bode plot for a low pass filter will look like this. A Bode plot for a band pass filter would look like this, and a Bode plot for a high pass filter would look like this, where in this case the low frequencies will be make softer or broken down, and the high frequencies will make louder. Same here, high frequencies down, this frequency down, that frequencies will be let through. So if we look at the Bode plot again, it means when you want a good filter, it means that pass band ripple must be as small as possible, so or as level as possible, so that all these frequencies are let through with the same amplitude, meaning that the measurements that you take are correct. You want your transition band as small as possible, so that only the frequencies that you want go through, no stray frequencies in this part. And the stop band ripple you will also want as small as possible. Mathematically it's a little bit more difficult. The smaller your transition band is, the more the bigger your structure is going to be. Remember that structure, let me just go to the structure. If you look at this structure, it means the more of these delays you'll have to put in. There's more of the shift register. So the better the filter, the more maths you have to do at the end. Alright, so if we want to design a filter, you have to now decide which type of filter you design, and this is the ideal formulas for that specific filter. If you want to use a low pass filter, you're going to use this formula, this one and this one. If you want to use a high pass filter, this one and this one. Band pass, this one and this one. Band stop, that one and that one. So normally all these tutorials and examples work on a low pass filter, so I think I'm going to be different. Actually do it on a high pass filter. So I'm going to use this formula and that formula. The next part we're going to look at is the window function. So you can either take, let's say, a high pass frequency, you're going to multiply it with one of these windows to make that transition better. Here we can see the stop band attenuation, main lob relative to side lob, pass band ripple. So this is the quality of the filter. So the better the quality of the filter, the bigger the maths. Can you see? So if you have to decide, are you going to do all the work and get a nice filter, or are you going to do a little bit less work and still get a decent filter? So these windows, it doesn't matter if you're making a high pass filter or a low pass filter, band pass filter. So with the previous one, this you're going to decide which type of filter it's going to be, and this is going to tell you the quality of the filter. So here we can see stop band attenuation. This means the part that you don't want, how much softer should it be? You can see 21 dBs, 44 dBs, 53 dBs, 74. If you think about something like a vacuum cleaner, maybe a modern vacuum cleaner, which is still very noisy, is about 74 dBs. Meaning if a vacuum cleaner was the sound of as loud as your noise, you would not hear this after the filter anymore. Alright, so if we look at our structure, it means we have to calculate these coefficients. So in my case, I want to do a high pass filter, so I need to know what that coefficient should be. So if we look at our formula, it means I'm going to use the formula for a high pass filter, which will be one of these two. And there we can see that's which HD is 0, which HD is not 0. So the value, if you look at the structure, it's not this specific one. We'll get back to it, but it means the one that's supposed to be 0, you'll have to use this formula for, and the one that's not 0, you'll use that formula for. Because the problem is that sample frequency is going to be in that formula there, and you cannot divide by 0. Alright, let's say we want to design a filter. In this case, I talked about a high pass filter. It means if you look at the transition width, it's 1500 in this case. That's the width of that part there. The cutoff frequency, it's 100. Means that where it starts to let the frequencies go through would be 100, cutting off this side. And sample rate is at 6000. So this is as quick as your processor is sampling bit by input. It's reading the voltage in at 6000 times per second. Alright, so even though this is in a Mathcad file, or you can do it in MATLAB, you can also do this on a piece of paper. And this example I'm doing now would be small enough for a piece of paper. So somewhere in a piece of paper, say you want to design a high pass filter with bigger than 50 decibels, it's the requirements. Your transition width must be this, your cutoff frequency must be this, and your sample rate must be that. And then I'm going to step through these formulas to the next formula. So on a piece of paper, we're going to write them down step by step, and you can work them out by hand with a calculator or an abacus or your toes or fingers or whatever, however you do maths. But as I say again, this sample is small enough to do by hand on a piece of paper. So let's look at the windowing function. They wanted to design a filter with quality where its stop band attenuation must be bigger than 50 decibels. So if you look at this one here, the Hamming, that's 53, so it's just bigger. And because it's just bigger, it means the maths, it's going to be just big enough. You can, obviously, if they want a better quality one, you can go higher, but then you have to do that. And you can see that's more difficult than that one. So we're going to use this one, 53. So from here, we get the following information. We get this 3.3 divided by n. We also get this formula here. So we're going to use this formula and this 3.3 divided by n. Alright, so let's look at the first formula there. Delta F, where you take your transition width, divide by your sample frequency. So that's how you get your delta F. So we have to get n. Remember that table that we got? We just get the table. This table says 3.3 n. N is the amount of delays we have to put in, basically, and that's the size of your structure. The better the filter, the more shift registers must be in. The bigger the structure, the bigger the programming. So we have to calculate how many n's do we need, how many shift registers do we need. So if I go back to this one, we can see we changed that formula just a bit. I'm rounding off, so I say 3.3. Where did I get that? I got that from there. Subject of the formula, if you still remember that from school. 3.3 divided by this delta F that I just got. So this one divided by this one, divide 3.3 divided by that, and we round off our answer. In this case we say 13, meaning we'll have 13, our structure must be 13 big. So it means this, you'll have 13 of these blocks that you need to add together. So there will be 13 addition sums that you need to do. We need to calculate 13 coefficients, if that makes sense. Alright, so 13, we have to look at the 13. The window function likes to go from a negative value to a positive value. I'll talk about that later, but that's how the windowing function work. That this table, this things like working from a negative to a positive. The theory behind it, it's going to take me another tutorial to explain, so I'm not going to go in it. We're just here going to do how to do it. So let's go to the formula again. So the formula 13, meaning 13, if you divide 13 by 2 you get 6,5, so it means we go from -6 to 6, where 0 is a value. So try and get this value always an odd number, so that you have not a comma there, not a comma there, because 0 counts as a position. Everybody get that? So if you'll see when you adjust your transition with always just a bit, so that this is an odd number. For an odd number you can go negative even number to positive even number, because 0 counts as a value. The next thing we're going to look at is then how to calculate the cutoff frequency. So the cutoff is what we want, but we need it as a relationship of my sample frequency, and there's a little bit formula there. That thing is called the smearing effect. So the smearing effect is your cutoff frequency plus your transition width divided by 2. So this is just a smearing effect. Again, the theory, don't worry about the theory for now, just do the formula on a piece of paper there. So by now hopefully you could have done all this on a piece of paper, and then our cutoff frequency, we take that 100, we say plus that divided by 2. Make sure that you do the plus and the minus the right way. You can't put that on top now, or else it will divide that one by 2 as well. Remember the basic school math rules. Divide by your sample frequency, giving you that new value there. Alright, so to know, we're just calculating the size of the structure. It's not a low pass filter yet, it's not a high pass filter yet, it's just the size of the structure. Remember we talked about that transition width must be as small as possible. There we can see it's quite large, so this is a terrible filter. The thing is, I want to give you an example that you can do on a piece of paper, but just to show you, if we make that smaller to really a narrow band, that there's no frequencies leaking through, as they say, you'll see that at the moment there's 13. To make it a better filter, you'll have to go a structure with 1032 values. So there's going to be the better quality filter, the better, the more calculations you have to do to get it. Alright, so I changed this back, so we've got 13 values. Everybody see 13 values. We calculated the FC. And remember with maths, don't just listen. Pause this video, write it down, see if you can get your calculations up until that point. The next thing, as I said, we want to do a low pass filter. So on the table, we go to low pass filter, and we get that formula there. We're doing a high pass filter now. A high pass filter, so it means we're going to use these two formulas. So the first value we need to do is the value for 0, and then we're going to do the value for 1, and then the value for 2, and then up until 13. There is a shortcut. I'm going to show you the shortcut, but for now, the first value is 0, then the next one is 1. So the first value is 0, meaning we use this formula, not that one. That's for 1 and on. This one is for the first one, 0, 1 minus 2 FC. There we go, 1 minus 2 FC. So we've got the formula for the low pass filter. The next formula we need is for the windowing function we're going to multiply it with. We decided Hamming, remember, for the quality of it. So we need that formula, cos 2 pi n over that formula there, because we used that one there, but we're now going to use that formula. So if you look here, we say that formula for the window function, 2 pi n, of which the n is 0, the big N is 13, and we get an answer. In this case it's 1. So what do we do next? We say low pass filter times the window function, low pass filter times the window function, 0.707 times 1 give me 0.707. That's our first value of the 13. I'm going to show you a shortcut so we don't have to do all 13, but theoretically, if you don't know the shortcut, you would have done this calculation, this type of calculation 13 times. Again, so if you get a better quality filter, it means if you have 1,000 value here, it means you have to do this calculation 1,000 times. So we calculated the first one now, which was for value 0. The next one will be for value 1. So if we go to the table, a low pass filter from 1. For 0 it was this one, from 1 onwards is this formula here, this formula here. So let's see how it works. There we go. WC, we need WC in that one. What's WC? It's 2 pi f. 2 pi fc in this case, so 2 pi fc. So from now on you can see for all the other steps it's going to be 2 pi fc. So that W there, you can substitute it already in there if you want. It's probably a better way of doing it. But here we can see 2 pi fc there. Fc, remember that's the Fc we calculated there with a smearing effect. The formula for the low pass, the formula for this stays the same for the window. Remember the window, Hamming window, that's it. Hamming window. So we get first we calculate the filter, then the window, and then what do we do next? We multiply the filter times the window for number 1, where that n is 1, that n is 1, that n is 1. Alright, so we calculated it now for 1, now we have to do it for 2. So we repeat the formulas, same formula for a low pass filter, same formula for the window. Only value is that n2 there, so that small n is going to be 2 for now, 2 for now, 2 for now. Remember capital N is 13, so we get the calculation for 2, the calculation for 3. Every time we calculate the filter and the window and we just multiply them together. The filter, the window, multiply them together. So that's the final answer we're going to use. We do this for, remember we went from -6 to +6, so if we just go from 0, if we go from 0, 1, 2, 3 and 5 and 6, that's the only ones we need to really do on a piece of paper, the first 6, because the negative values is going to give the same answers. I'll show you now. Alright, so I showed you, we calculate the value for 0, for 1, for 2, up until 6, and these are the values we get. Just remember the 0, 1 is not 0, because we had to replace that formula. And here we get it, 0 was actually 0.717, the one for 1, the one we got there was -234, so that's the value. We got the values for 6, and what do you note? The minus values are the same values, just in a different order. So it means if you have a value from -6 to 6, it means you only have to do the positive side and just repeat it for the negative side. So you only have to do half the calculations. That's the shortcut I was talking about. So before you go further, try and do that first 6 calculations by hand. See if you get the same values. You might get a little bit different depending on how your calculator will round off, but it's going to be close to this. So see if you can get that 6, then repeat it like this. And then if you plot it, you're going to get a graph that looks something like this. Again, that 0 is wrong. It's supposed to be 0.707. And an interesting thing, and you can go in the theory later, if you do a Fourier transform on this one, if you get this time domain in the frequency domain, it will actually show you your boat plot for your filter. So a quick recap. You want to design a filter. The filter must be of this quality. So you look on the tables, you say a Hamming code is going to do that quality. From the Hamming code I get that formula there, that 3.3. The next thing, I want a low pass filter or high pass filter or band pass filter. In my case, a high pass filter. Of which ranges, because you have to decide where your filter must be. So your cutoff is going to be important, your transition width is going to be important. Sample rate, the speed of your processor. So these will be given. Quality of the filter, how big the transition width must be, which is also an indication of quality. Sample, where the cutoff must be, and how fast your processor. This is given. The next thing, these formulas you must well know or just copy from this tutorial. There we see the first formula we're going to calculate is delta F, which is transition divided by Fs. The next one we're going to substitute, make n the subject of the formula from our table about the, in this case, Hamming window. This is to calculate how big our filter should be, how big our structure should be. Case 3.3, this I got from the table, divide by that one there. We round it off. 13, again, make this odd so you can go from an even number to an even number. The window function likes negative to positive, so that's why odd number here. So make sure your transition with, if they give you something else, just tweak it a bit, that it's still in specs, but that it rather gives you an even number there. So now you've calculated the n size. The next thing is to calculate FC. How do I get FC? You have to do this formula FC. So cutoff plus, this is for smearing effect, so just know this formula. FC plus TW, which is my transition width, divided by 2, divided by FS, which is that one. You get a new value for FC, our new cutoff, which is kind of normalized to a smearing effect. If you don't understand the theory behind it, don't worry, just do it. Okay, so the next part is for my first value, which is value number 0. For value number 0, remember on the table there was a formula, in this case a high pass filter. The formula for the 0 for the high pass filter would be that one. The window function, because we're working with Hamming, we decided on that one because of the quality of the filter, and that 3.3 that we read from the table. If you choose another filter, you must use a different value there. We use that formula there, so you just calculate, and how easy is that? 1 minus 2 FC, that C there, 1 minus that, you get an answer. In this one you substitute 13 there, 0 there, that's a 0 there now. You just calculate with a calculator or an abacus or your toes, get a value there. What's the next step? You multiply the high pass filter with the window, you get your first answer, the first theoretically of 13. Alright, so we calculate the one for 0. We're now going to calculate the one, the first value with n is 1. That's a different formula. Remember on the table there was one formula for where it's 0, one formula where it's 1. Again, the maths looks complex, it isn't. You can just say sine n. The WC, that's 2 pi FC. That FC you calculated on top. The small n in this case is now for 1. Capital N still stays 13. Then you do the same calculation. Remember the last, you take the filter times the window, filter times the window to get the actual final answer. You do it for 1, 2, 3, 4, 5, and 6. Remember we go from minus 6 to 6, but if I showed you here that if you just do 0 up into 6, you can see minus 6 has got the same answer as plus 6. So you really just have to do half of them, repeating it there. Now we get to the structure. It means we have 13 of these. And that value, I know it says H0 there, but because we use a windowing function, we actually have to add 13 to our n here. So you go, wait, say again, what did you mean? Yes, if you don't understand maths and I say like add 13 to your n, what it actually means is that value for minus 6 will be the first one. So all that you do is, that value is your first one there, and that's your constant you're going to multiply with there. That one will be there, that one will be there, that one will be there. So just start from the top, filling in those constants in your program. So if you use maybe assembler or different type of programming, you take your input value, maybe that's a 2, you say 2 times that value, you get an answer. One sample back, whatever the value is, one sample back. If the value of now is 2 and the previous sample was 3, it means the value of now was 2, the previous sample was 3. So then 3 times that value there, plus 2 samples back times that value there. So you can see it's just now sample plus the previous sample times that plus the sample before that plus, and we're going to do this for 13. So if we look at the structure, you now realize that this filter, although it's a real-time filter, meaning when it's running it will run, the first few steps of it won't be a stable filter, because if you switch on this machine for the first time, these values will probably be 0, meaning your filter is not going to work in the beginning. So what you need to do is you have to wait until these shift registers are full before it will process as a real-time processor, if that makes sense. So normally on expensive sound systems you'll only hear your speaker switching on after a bit, because these filters are actually switched on. If you do some sort of graphic equalizer on your PC, you can always hear it takes maybe a few seconds, but there's a definite time delay after you made your decision. So after it calculated the coefficients for you, placed it in there, you'll see there's a time delay before you can actually hear the answer, because it actually waits for all the shift registers to fill in before it starts doing the filter. So it's a real-time filter, but it's not a real-time adjustable filter. Alright, let's look at the LabVIEW program. In LabVIEW, I just draw the structure. Let's go to the structure. Can you see that's the structure? My delay blocks, my first constant value, second constant value, third, and I just add them together. So there's my constant values that I just multiplied with and add them together to get my final answer. Again, this is going to be different on your, if it's assembler, this was done in code. If it's C, it's done in code. So remember, you have to program this structure in whatever language you're working in. So let's look at my simulated signal. I'm simulating a signal here at 6,000 samples per second. So one sample at a time. So it's like you taking a multimeter or something and measuring the voltage one value at a time. So what's the voltage now? What's the voltage now? Or what's the temperature now? What's the temperature now? But you're doing it 6,000 times per second. So obviously it's a little bit faster than you can do it. But this is what all PCs work like this. They do not work continuously. They've got a certain speed that they get one value at a time. So you can either store a lot and then do the calculation on, or what makes this finite impulse response filters nice is, as it's measuring the input, it's got enough values in which you did store it in the past, but it's got enough values to calculate either the average or the coefficients so that it will make an immediate answer for you. So as it measures now, it's going to give you an immediate answer. Let's look at the delay value. This is basically a shift register, so it just takes one history value back. So if this is my value coming in now, let's say it's temperature, we're measuring temperature. It was this morning it was 6 degrees, now it's 20 degrees, so it depends on your sample rate, but this is the measurement now. What's the measurement now? That was the previous measurement. That was the measurement before that. What was the measurement before that? And all of those single measurements we just multiply with the coefficients that we calculated from the Mathcad there. So remember, we started with a -6 one first, so that's our first one. See, that's the first one. Then the next one is 12 and 12. So we go, we go 12 and 12 minus 21. So remember, with this one, we calculated this from 0 to 6, then we just repeated it from -6, can you see, but in the opposite direction. So 0 to 6, and then we used this -6 one as our first value in our structure to numbers 13. So this becomes our first value, second, third, and so on up until 13. Why 13? Because we calculated it as 13. Alright, so this block here, this just calculates the Fourier transform. So I got a time domain, Fourier transform, frequency domain. So if we look at the application, here's my application. Time domain, there's my frequency, and we can see at the moment I'm just adjusting it there to 1,000 hertz. We can see the peak there, well, it's close to 1,000. The peak there is on 1,000, so we can see the Fourier transform just as a nice indication to show us how where the frequency is. So there we can see this is my time domain, that's my frequency domain. This is before the filter, and then this one is after the filter. So we can see that the high frequency is going through. Remember, our cutoff was 100, so if I take this to 100, we can see how close I get to 100, the smaller it gets. So that frequency is completely taken away there, and the moment I get to 100, we can see the frequency with the transition width is going through to the end, making it a high pass filter, because the high frequency going through, low frequencies are stopped. Alright, so this is how you design a filter, a FIR filter. So you need to know your structure, you need to know how to program that structure in whatever language you have. But you'll see it's just, you just add, multiply, add, multiply, add, or multiply. If I go here to the structure, and we just need to calculate those coefficients. So the structure will always stay the same. The coefficients will change depending on what type of filter you design. So if you did the open air speaker system, you would have made these for your cutoffs for your sample rate and your cutoffs and your transition widths for maybe a low pass filter for your subs, a high pass filter for the tweeters, and a band pass filter for the stops. You get all the rest of the information from those two tables that I showed you. Remember these two tables. So for your low pass, you're going to use those formulas, high pass those formulas, band pass those formulas. Then the window function, you're going to decide which window will suit your quality the best. I like the Hamming one. We can see there, from here we'll get the formulas that we need. So the window formula, and then that 3.3n to calculate the size of your filter. So what's next? You use that, in this case 3.3, to get the size of the filter. We divide it by that delta f. Delta f we got with this formula. From there we get our new cutoff frequency with the smearing effect, so we just apply that formula there. Our first value, let's say for a high pass filter, we get the formula for my filter from the table. N0 from the table, you see there's a formula for 0 and the formula for the rest. The formula for 0 is this one. We multiply it with the window one, we get the coefficient value. So the filter times the window gives you the coefficient. Try doing this by hand, as I said. Then we do it for one. From 1 onwards, we use this formula instead of that one. Again, filter formula times the window formula will give you the coefficient. We only do half of them because we're going to go from, in this case, -6 to 6. So we'll see. If we only do from 0, 1, 2, 3, 4, 5 and 6, we get 6 values there. We can repeat those 6 values as our minuses, and then that in our structure we start from the top. So our first value there would be the one for -6. Even though it says H0 there, what you actually do is you have to plus your n with your big N. So this would be your new 0 value, and so onwards. So the values that you calculated there, you just come in there, and we've seen in the software program that's in your type of software, but we've seen in my software that this was actually a high pass filter.